Okay. So have your change. We measured the fundamental frequency, we measured the period. But then from that, we know the fundamental frequency, the tension and the length, so we know all that. I need to tell you, frequency is about 7/10 of a cycle per second, if I recall correctly. Tension is from the 500 gram weight is about ballpark 5 newtons, probably 24.55. And the length is about, I think, 4.6 meters. That we got the chain right there, we can remeasure it if we need to. Okay. So I'm not interested now in what we do with the numbers, but I want to know from what we have, can we determine the mass of the chain? Okay? Not in terms of numbers, not necessarily in terms of formulas, but what's related to what. So the question is, forget that we're looking for mass, ask what can we find? What's the most obvious thing we can find from all that information? Okay, we got some pretty good answers here. And I didn't have to do too much writing. Did have to prompt you, the first few problems in that set. Deal with frequency, wavelength, and so forth. So if you know the frequency, you know the wavelength, right? So that's automatic. I'm sorry, if you know the length of the chain, you know the wavelength of the fundamental. And you put that together with the frequency to get the velocity. Okay, so the answer I got was, frequency, velocity, get the wave velocity. Now the question is, well, how do you don't know both of those things. You're not given both of those things, but you're given the length of the chain. And then got a pretty good answer. I think it might be from something that was written down rather than a picture. But it's still a good answer. What's the picture that allows us to determine the wavelengths and the length of the fundamental of a chain fixed at two ends? Okay. Well, somebody said something about nodes and antinodes. That's good. Okay. Get down to the gut level. The picture is here are the two ends, and your shape of the chain goes from here to 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 here, right? Now you've got two waves approaching. And this is your model, which is though you have two waves approaching. So since you're continuing to stimulate this thing, it's like there's a wave coming from this end. Okay. Because the effect is totally equivalent to that. And the reflected wave comes from this end. So at one time, the reflected wave might look like this. And of course, it keeps coming. Well, when that reflected wave is here, this wave is here, and they go together in such ways to cancel each other. Okay, is that reflected wave moves in, and the wave moves. Okay, the reflected wave comes at you, and this wave moves in the positive direction. Okay, they combine, and the question then is, what's the wavelength of this originating wave and the reflected wave? Well, you see that this is one arch of the sine wave or cosine wave, whichever one you want to look at, okay, whichever one you want to use. And one arch is half of the total wavelength. Okay. So you really want to see that in terms of all the pictures we did last time. This is the reason you get this. Now you don't actually have a virtual wave coming from here. You don't actually have a wave coming from here, but you can model it in terms of those two waves coming through and meeting. So like at this particular time, this wave is gonna come through like this. This wave is gonna come through like this. And the chain is gonna be flat. So he moves a quarter of a wavelength, this thing moves a quarter of a wavelength, and all of a sudden they're reinforcing. Okay, you can draw that. You did draw that. Okay, just focus on one node to node section of that bigger picture. Okay, so there it is. That's your model of a harmonic wave. And if you're doing the second fundamental, the second harmonic, okay, you'd have, your wave would be shorter. And we didn't draw a shorter wave, we just looked at two nodes and further apart, but it's the same thing. So you'd use a shorter wave and it would reinforce and so forth. It would have half the length. So you'd have half the wavelength, so the full wavelength would fit in there. So make sure you understand that picture. So anyhow, so that's pretty good progress. So what can we find? Okay, so okay, well, this is L. I can write that down in symbols rather than words, but the wavelength is double the length, or the length is half a wavelength. Okay, so actually, if you're reasoning it out, you don't want to make that big jump. You say L. Is that, and lambda is 2L. So now we're going to write around words rather than formulas. Propagation velocity is a wavelength times a frequency. You want to think that, you want to visualize that. Okay, wavelength is this much. The frequency is 100 cycles per second, so you have 100 times this distance in a second. Okay, you multiply the frequency by the wavelength. So you could say now C equals lambda L. Good formula, but you don't want to use it without making sure you understand it. Okay. I mean, yeah, if you're on a test and you got to get the answer, and you got to grab the formula rather than thinking about what's really going on. Maybe because of time pressure, if you got a time limit. Maybe because you've been there for 8 hours already and you got to go eat. Your brain's getting fuzzy. Okay, there are all kinds of reasons you pull out the formula, but think in terms of the idea and the picture. You can do more that way. Okay, well, that's progress. Okay, so now we know the speed of propagation. So, how does that help? Well, we're practically there. But you tell me, and somebody already said a lot of it. Okay, very good, quick answer there. I hope I would. I was expecting I would. Would have been terribly disappointed if I hadn't. Everybody pretty much nailed it. Okay. How does mass come into the picture? Well, the speed of propagation is involved with the tension, the length, and the mass, right? So okay, I'm going to use this word relate. We're going to try to get used to thinking about what things are related. By relate, that means these things are related by a single relationship. Okay. We know that relationship, everybody knows it. Okay, I've heard it out of everybody's mouth. Yeah, maybe not yours, but you didn't inquire for that. Okay, no, I'm sure everybody knows this, okay? So how do they relate? Well, if we know three of them, we can find the other one. Okay. We know all but one. We can find that one. Okay. Now at this point, okay, it's safe to write out the equation. First, derive it in your head using the impulse momentum theorem, then write it down. That's a tricky derivation at this level, okay? And I don't know what's going on, but I don't know how long I've been writing. After the camera chose to zoom itself back to the origin of species or whatever. Kind of irritating quality of this camera, which is otherwise wonderful. You know, I shouldn't be flipping this thing around while I'm recording. Okay, actually, I'm live. I'm going to try to, that goes up too far. Comes down just about right. I'll leave with that. Move it over this one. Maybe I get this in. Don't lose that. Oh, sorry to be doing this in the video, but I'll do that actually every once in a while. Okay. So we can write down an equation. At this point, that's appropriate. Let's see. Write that down, solve for n. Okay. Let me check out the units. Want to be an engineer, you write everything down without units, and then hope you got them right. I prefer you in physics class to write out the units. Okay. But they will work out. You're going to get units of velocity, SI units of velocity, if you use SI units of tension, mass, and length. So just looking at the numbers, tension is like 5 newtons. Mass, we don't know. Okay. Length, well, we solve the equation for M. We got M. Should have done that first. M equals tension over LC squared. Square both sides. And then just multiply by M, divide by the C squared that you get. And check out the units in case you did the algebra wrong. I'm not trying to do the algebra right. Let's see if we get a reasonable result. Okay. If we find the chain has a mass of 500 kilograms, it just means we're all a lot stronger than we thought we were. We had no trouble manipulating that chain. Okay. So if we come up with 500 kilograms or something like that, we know that something's wrong with our calculation. Okay, well, now tension is about 0.5 newtons. Length is, let's say, ballpark 5 meters. Okay. Speed of propagation. I mean, the wavelength is like 9 meters. Frequency is like 0.7 cycles per second, right? So that's like 7 meters per second. So C squared would be 49 meters squared per second squared. And that's not enough. We got about 20 grams. One more than that. So something's wrong, so you all figure out what's wrong and fix it. Either the data's wrong. In other words, the numbers I'm using here are wrong. Okay, or solve the equation wrong, or wrote my this equation wrong. I'm sure I didn't do that. Okay, solve the equation in my head, but it seems pretty straightforward. Uh-oh. I did I solve the equation wrong? What did I do wrong? Somebody tell me. Well, yeah, I pretty quickly saw what I did. And you all probably saw it a lot sooner than I did. That L would go up here. If the L was down here, the units were not going to work. I didn't check the units. I just decided to check the numbers to see if I solved it right. Okay, see if I got a sensible solution. Well, I didn't get 500 kilograms. I got 20 grams, which is not quite as ridiculous as 500 kilograms. But if you think about it, the chain weighs way more than an ounce. Okay. Okay, so now we have tension times length over c squared. C is still around 7 meters per second squared. Okay, so that'd be 49 meters per second squared. Length of the chain is about 5 meters. That's about 5. That's 25 over 49. Okay, which is real close to half. Kilogram. And that's for the reason. Turns out that's the suspended mass, but that's just coincidence. Okay. Now, those are ballpark figures. Okay. Like 7/10 of about 9 meters is more like 6.3 meters. If you square 6.3, you get about 40. So you'd be dividing this by 40. Tension times length would be 5 times 420 divided by 45. It actually kind of makes it worse because I know the mass is a little less than that. But work it out for your data. What you do, I'll reward you by 1%, which I've already done. I don't remember exactly what it was. There's significantly different on half a kilogram. And if it comes out different, then think through the physics and ask yourselves, what could be wrong? Okay. Is there something wrong in the way we executed the experiment? There's something in the apparatus that we didn't account for? Like maybe the friction in that pulley is a whole lot more than we thought it was. It's not. It's a little, it might be more than we thought it was, but it's not enough to account for that. So you could say, okay, well, if the tension of the pulley, if the coefficient of friction in that pulley was like 0.2 instead of 0.003 or whatever it might be, well, we know it's not 0.02, we can measure that. Okay. We could hang equal masses on both sides and then add mass to one side and see how much extra it takes to make the thing start to accelerate. And we can estimate the coefficient of friction that way. So we could probably eliminate that. What else would we do? Well, we pull out everything we got. Trying to figure out what went wrong. Engineers do that too. And they design something, somebody builds a prototype and it doesn't work. And go back and debug things. Okay? And it happens all the time. You have a plausible prototype, your whole team believes it ought to work. And then there's some off the wall thing nobody thought of. And probably nobody would be expected to think of, and then you learn something. Okay, well, that's why we learn some physics. Or we learn to analyze things. Okay. And you learn on the same thing in engineering, just in a different context. And I'm pretending I know about engineering and I really don't. Yeah. Engineer things in physics, I think that's totally different. power systems, or buildings, water treatment plants, chemical plants. Okay. Okay. It's not a particularly complicated thing. Y'all did well with that. But think in terms of what does all this tell us about the apparatus and about what we observed? And also, if we didn't come to the conclusion that's consistent with reality, why not? Okay, so I just went on a little digression about weighted averages and average values. And why is it that people have trouble understanding average values even after calculus class? And have trouble remembering anything about it. So we're gonna end up, I think, with an average value here. Okay, so what we've said so far is that in a traveling wave, every particle undergoes simple harmonic motion with the same frequency and the same magnitude. So the total energy is just the total energy of that simple harmonic motion. And that total energy is just the kinetic energy when it goes through its equilibrium position. So if we know simple harmonic motion, which y'all did pretty well with in the final, hopefully you remember some of it. Okay. We can easily, if we know the amplitude and frequency, find out the maximum velocity. So every particle has a maximum velocity, but at every point in the simple harmonic motion, its total energy is the same as it is at equilibrium. And what is up here? It's all potential energy. It's energy. Energy is in the wave. Okay. That's stored in the medium. So in the case of a traveling wave, the total energy is the same as if the whole mass of the wave is undergoing simple harmonic motion, even though different parts of the wave are moving in different phases. The whole wave doesn't move, because the whole medium doesn't move like this, but it's still the same total energy. So it's a more sophisticated derivation of that in your book. It's worth looking at. But that's sufficient for what we're doing in this kind of quick summary of waves. Okay. If you have a standing wave, then at any instant, okay, here's the shape of the standing wave. Okay, here's maximum amplitude. Right. Then, if this is X, let's go ahead and put your Y-axis here. Then this wave has a form. Y equals A sine of KX. Make sense? Well, what's K? Well, I didn't give you any numbers. Okay. So we're going to say that, and we're looking at the fundamentals. So right now we could just say that this length is L. So now what's K? Okay, well, I can complete the cycle out of here. Okay. So I can say we complete a cycle, don't we? Pretty obvious. X goes from 0 to 2L. If your wave is in fundamental mode, on a median of length, so. That's what it's going to be, okay? Whatever it is. Okay, in this case, though, if X changes by 2L, we complete a cycle. So. How much does KX have to change by to complete a cycle? Can't say, but I'm gonna drag it out here. Or maybe you know. Okay, the answer is so obvious, nobody wanted to say, but all of a sudden everybody said it together. I think y'all are just pulling my chain. Okay. Had a fundamental frequency. Okay, so we complete a cycle, so. KX changes by 2 pi. So what's KX? Or what's K? Okay, so put this together, but it's an important picture, so you really kind of want to understand it. Okay, times 2L has to equal 2 pi. Okay. Because if X changes by 2L, then KX changes by K times 2L. The KX changes by 2 pi. Now, don't confuse this by how K is related to lambda. Okay, we could also say, I'm going to be cautious. X changes by lambda. AX changes by 2 pi. So K is 2 pi over lambda. Okay. So this special case where L is half of lambda. I mean, it's actually pi over half of lambda. Okay. Which is 2 pi over lambda. So I'm going to say K equals pi over L equals 2 pi over lambda, which is more general. I'm just talking about fundamental here, so just talking about one arc of the sine function. And this works, but we'll do it in terms of lambda. Okay. Now we see. When I wrote that, this was an X here, it almost looks like a lambda. I had to squeeze it in. 2 pi over lambda times X. Okay. Okay, well now, we want to know the energy of the simple harmonic motion at some interval delta X. Okay. Now, in calculus, you learn to set up integrals. You learned it at least temporarily, so you could do it on a test. But, you know, my own experience, it took me into my sophomore year before it really gelled and made sense. So you're right at that stage where it should start gelling and make sense. What we do. So we have an interval delta x. With a sample point x star. I don't like labeling it, so I need to draw a vertical line for that point, but I really didn't leave myself a lot of room for later. So, x star is just any sample point within the delta x interval. So what's the amplitude of motion at position x star? It's just the value of the function at this point. So you have less amplitude for the particles here than you have the particle here, and maximum amplitude per particle here in the middle, and that's the amplitude of the wave that we measured at the center of the wave. Okay, so we looked at the center of the wave there and saw it moving about that far from equilibrium, about that far from one extreme to the other. We estimated an amplitude of 10 centimeters. Remember doing that? Depends maybe where you were. You weren't standing there at the center looking at it. You're looking at it from a distance. You might not remember it, but we did that. Okay. So okay, it looks like maybe it's 10 centimeters because that's a nice convenient number. So there's the amplitude. Okay, well, so how much energy is there in that? Well, I'm out of board space, but we'll continue it. Here. Well, what do we need to know to find the energy of a simple harmonic motion? Okay, so we're trying to get to the maximum kinetic energy of the motion of just this segment, which we assume to be a very small segment, so that the amplitude at every point is very close to a sine 2 pi x star over lambda. Okay. Okay, well, what do we need in order to figure the simple harmonic motion? So that the energy, the maximum kinetic energy of simple harmonic motion. Okay. Now, two ways we can get the maximum energy. You get the 1/2 Ka squared, which is the maximum potential energy. Just integrate Kx 0 to A. Okay. You can want to know that. We'll think about that statement. But we don't have a good way of doing the potential energy here. There's a way, but we don't have time to do it. And you probably won't see it right now. Okay. Much more easier, much more direct to figure out the maximum kinetic energy, because in simple harmonic motion, maximum kinetic energy occurs at the equilibrium position, and all you need to know to get the maximum velocity, at least, is frequency and amplitude. You just think back to y equals a sine of kx. That will make a sine of omega t. It's a derivative of that, negative omega a cosine of omega t, right? So you made omega A, since the cosine of omega t can't be bigger than 1. The magnitude of omega A is it omega times A, angular frequency times amplitude. That's your maximum velocity. Okay. So you can do that. As far as mass, well, if we know the mass per unit length, we multiply that by delta x, right? So let's see, let's let you equal mass per unit length, a very common way to do that. I think we both maybe does. Okay. Many authors do. And I kind of like it once you understand what I know you understand about mass per unit length. Okay. Delta mass of segments u delta x. U delta x. Maximum velocity is omega A. Okay. And omega is just f over 2 pi, right? Is that wrong? 2 pi out. No, wait. See, I'm already mixed up in that. I've got to figure out what the difference between omega and f is. Omega is number of radians per second, f is your number of cycles per second. So you get more radians per second than you get cycles per second, so it's 2 pi f. It's actually built right once I said it wrong. I want to understand that at the level of unit circle, radian versus cycle. Okay. Otherwise, if I can get mixed up on it, I believe you can. Okay. I don't memorize formulas, I remember pictures. They need to do both. Okay. Make sure to the greatest possible extent that you can put the formula together with why the formula is. Anyhow. So maximum kinetic energy of the segment is ½ its mass times its maximum velocity squared, right? And I'll call that a delta M. I should have been a note. Okay. And that's now. Dangerous thing here is just using A. A is a function of X. A is different for different X's, right? So maybe to be safe, I better call that A of X. Well, the 1/2 and the 2 here go away. You get the mu delta X F. And it constitutes a square of this, right? So it's going to be a 2 mu delta X. If I square this, I'm going to get a 4. And I should have written my pi squared in there. I didn't. Then I can get my mu pi squared F squared. Notice I didn't write my delta X, and I want that out here at the end. So I'm saving it. I'm going to forget it. I don't think I will because I'm going to need it. And then the A of X is A squared sine squared 2 pi x star over lambda times delta x. So the sum of your 1/2 m v max squared is root pi squared twice. Remember, A is the actual amplitude of the fundamental oscillation. This distance out here at its maximum. Okay. Make sure I got everything. Then it's times the integral. So sine squared of 2 pi x over lambda dx. Now we think of partitioning the interval of the fundamental. We chop this thing up into a bunch of little delta x blocks, each with its own amplitude. So we're summing up all the sine squared of 2 pi x star over lambda L times delta x. And that leads us to the integral. You want to definitely review where integrals come from, because among other things, we're doing our first set of integrals in polar variable calculus tomorrow. So this whole partition process, you're going to see it again tomorrow. Arc length. Okay. So you want to probably review that, read over it in calculus 1. People don't say their textbooks, but you can find it online. Okay. If you do have a textbook, I'm happy to be able to open it up and know where it is rather than out there in the ozone. But if you know what to search for, you would always ask ChatGPT to review it for you. They do a pretty good job, I think. Haven't asked it that one, but so I think it would. When you're little, I've seen it, but okay, well, anyhow, you got this, okay? So you've got to be able to integrate that. You know, the integral of the sine squared of a quantity over a full cycle or half cycle is half is 1/2. Then you just get a 1/2 out of this. Uh-oh, I have 1/2. I got the 4 pi squared. Should be a 2 pi squared here, unless I've got, unless I'm missing something probably. We got the half u delta x, and we got a 4 pi squared here. Should be a 2 pi squared. Anyhow, you know, it's the integral of the sine squared over any half cycle or full cycle is actually not 1/2, but 1/2 times the length of the interval. Because the average value of the sine squared over full cycle is 1/2. Worth proving, worth understanding. Then you can shortcut this and you get the usual expression. Okay, and you don't even have to worry about the 2 pi x over lambda, since lambda is too little. You're doing this is half. From 0 to L gives you half a cycle. So it's the average value of the sine squared of 1/2. Okay. And check me on that, you know, make sure that I haven't done it. But you know your head. It's hard for me to do that. Okay, it's an important process, important idea. And of course, I'm not going to ask you most likely to do the full derivation like formula. It'll give you enough information that you can. Well, for homework, I'd ask you. To use the formula, to determine how much energy we have to use. Get that thing into some harmonic motion. First thing you can go to the energy somebody has to use in the gym. Get those stupid ropes moving in simple harmonic motion. Okay. I need to pick up one of those. I can't do that. Shoulders in that way. Something isn't quite right. That one. Shoulder goes into this texture. So I destabilize it. I did that. But I see people doing it and I see them getting red in the face pretty quick and they're in pretty good shape. Okay. So there's a lot of energy, you could actually count that. It'd be kind of a neat thing to figure out. Next time I see somebody doing it, I'll make some estimates of frequency. I can estimate that about like this. Okay. So that's about one complete cycle per second. Then their amplitude. You don't really get a movement and a pretty good amplitude. And if we can do a little bit. Okay.